Okay, here's a quick run through the other examples. So we're going to take and graph this thing first, put in some t's. First you need a domain. Sometimes it'll be given to you, t for t's by the parameter t. T is from, this value to that value. Well, this one, if it's not given, it's the shared domain between these two functions, x and y. And for sine and cosine, the domain is all real numbers, negative infinity to infinity. So we're just going to go with that. Now, it doesn't mean I'm going to pick all those. I'm going to pick some easy ones, and that's just usually the rule of thumb. If we're going to graph this, pick some easy ones. 0 is a nice easy one, so cosine of 0 is 1, so 2 plus 3 is 5, and then sine of 0 then, of course, is 1, so negative 1 plus 2 is, wait a second, plus 0, sine of 0, sorry, sine of 0 is 0, so negative 1 plus 0 is negative 1. That's a nice easy point. Pi over 6, I don't know, try something like that. Not as easy, but if you look carefully, I wrote that in. That's okay. 3 radical 3 over 2. 2 plus 3 radical 3 over 2, and 0 for y. Put in the pi over 6, radical 3 over 2. And for sine, what do you get for sine of pi over 6? That height there is a half, so 2 times a half is 1, negative 1 plus 1. Yeah, that's not too bad. Pi over 2, that looks good, so try pi over 2. Cosine of pi over 2, of course you get nice looking, 0 in there, so you just get 2, and sine of pi over 2 is 1, negative 1 plus 2 times 1 is 2, so yeah, that's nice. So you're getting the idea. Pick some easy numbers, and then plot as you go. It's a little easier to see, because then in sequence, you can kind of see where that happens. I plotted the two easy ones, like 5, negative 1, and 2, 1. And then you'll notice that 2 plus 3 radical 2, comma 0. That you can kind of see where that would hit in there. Ballpark. I just put a little arrow there to show where that's at. But in order, as I plotted these, you can see the arrow is kind of telling me that's the direction going to the left there that this is plotted out. Just keep going. Looks like pi over 2 multiples. Those quadrangle corners, go around the circle. So let's stick with that. Let's go pi over 2 increments. So we'll go pi, 3 pi over 2, 2 pi. Okay, nice deal. So we got these relatively easy values to plot, and then we have a sense of direction. And if you notice, whoa, 2, 1, and then we go to this negative 1, 1, and then we go 2, negative 3, and then we get 5, negative 1. We're back where we started. We did a loop. Kind of looks like an elliptical kind of deal, and that's actually kind of what we've got going on, and that's good insight if you were thinking ellipse, footballish, or maybe orbit of a planet around an object like a sun. So notice that elliptical nature, because that's actually at the root of this. We're going to find out this is actually an elliptical function. We're going to see how the actual graph of it, the function as we know it in the xy coordinate plane, is elliptical. So if you're thinking ellipse, you have to remember things like, all right, when there's a center, there's a distance to each edge. There's like a major and minor axes you want to look at, so up to 2 vertically and 3 horizontally. Those two values play into the elliptical formula. If you don't remember, let's bring that back. So h and k are the center that I just got 2 and 3 in this format, and a and b are those axes, the 2 up and the 3 left and right. And when we place those in there, we get a nice little function. And it's all equal to 1. Remember, see, these conic sections are functions equal to 1. So horizontally, 3 was our axis there. That corresponds to a. It goes along with the x variable. Vertically, 2 goes along with our y variable, so you got 2 squared underneath there. And of course, center was 2, 3. And I think, did I write that in there right? That is weird. So my center, it's the actual point of, I got to mark that right. The coordinate of the center is 2, negative 1. So if you notice 2, negative 1, I didn't even read my own writing, then that's the equation with center hk 2, negative 1, and a and b being 3 and 2 respectively squared. Nice little function, right? Well, how does this relate to what we started with? What's this parametric have to do with it? Well, take a look at the values in there. The center, 2, negative 1, is hidden discretely, as you can see there. And then what about a and b? There they are as well. They're snuck in there. Well, let's put it together. In this case, when we came up the xy function, the xy function or the curve that we could to represent it with, last time we eliminated the parameter by solving for t in one of them and then substituting it into the other. With sine and cosine, we do something different. You actually want to solve for cosine and solve for sine. So let's pull it onto the next page. You're actually going to solve for sine and cosine in each situation, and what we're going to use is a trig identity. There's many of them, so we're going to have to pull those forward. Once we have that trig identity in mind, we're going to use that relationship to end up coming up with our function. So we're going to solve for cosine of t, and then we'll solve for sine of t, as you see here. So just a little bit of algebra to get those in order. Then we're going to use the trig identity that would relate those two, sine and cosine, and the most popular, of course, is our Pythagorean identity, sine squared and cosine squared add to 1. Then if you substitute in the functions that we had, do some squarage, get that all in order. Hey, that's interesting. Take a look at that equation. Just that one substitution, do you see something? That's the function we got before. So it's the trig identity that pulls it together. In trig functions, don't solve for t, solve for sine or cosine of t, and then we'll use an identity to go from there. Okay? So pretty groovy. Like throwing these at you. Brings back some old memories, doesn't it? Moving right along, we have, what if I want to take a derivative? We've talked about this rate of change, how fast it's moving, is obviously something we can kind of infer from the graphs that we've looked at, but now we need to get down to business. Let's just do it. If you want dy dx, that's the slope of the tangent line at any point c, or I say a curve c, so somewhere along that curve at a certain time, you actually take the derivative of y with respect to t, and then do it divided by the derivative of x with respect to t. If you prefer prime notation, you could call that, as I've noted here, y prime t over x prime t. That's the idea. And if you do a little fancy-smancy, dividing these two ratios, you'd see the dt's cancel if you multiply by the reciprocal. You can see the equivalence of this expression. The idea is to get dy dx, the slope of the tangent line, you want to do the y prime of t over x prime of t. Second derivative, which you see down below, actually is a means of just taking the derivative of the y prime function again, and then dividing it by plain old dx dt. So the second derivative really only requires that we do two derivatives of the y prime function and then divide it by dx dt. Easiest thing to forget, dividing by the dx dt when you're done, that x prime of t. So be careful. We'll look out for that. In me too, so you want to watch my work. All right, let's do dy dx for this example number 4. So that means take y prime of t first. Got it. So little 6t minus 2, then do the derivative of 2 radical t. Of course, you want to change that to 2t to the 1/2. And its derivative would be t to the, that should be a negative 1/2. Did I not write that in there? I don't know. I got to get that up there. So that should be a negative 1/2, so I can bring it up to the top. So if I zoom way in here, let's get some blue action into my drawing. I can do this. Focus, focus, focus. It's like being a ninja scriber here. There's a negative. Sorry about that. So by flipping it up top here, you make it a nice negative. I think that all works out. Yeah, does that look like good a calculation? Yep, we're in business. That's a negative 1/2 from taking that derivative. And there you are. There's dy dx. If you simplify, simplifying is, early and often is always the name of the game. It's if necessary, do it, and often it is, especially if you're going to take another derivative, get it simplified. So once we have dy dx, now you know, hey, all I got to do now to get the next derivative is take the derivative again, but don't forget to divide it by x prime of t. So here's that piece. So let's do the derivative again at the top. Okay, so I got that. But don't forget, you're going to divide by, this is the big deal down here, this one. Take the derivative again, and then divide it by x prime of t. And I don't know if I stated that carefully up top here, but this is, just take the derivative of dy dx again, and then divide it by dx dt once you're done. So that's what we've done down here. I feel like I might have said something else that was funny. I don't know, you can let me know. But the idea is take the derivative again, but don't forget to divide it by x prime of t again. Beautiful. Thanks for hanging with me on that one. So now, on we go. Let's evaluate it. It says that t equals 1. So let's put some numbers in there, see what happens. Simplify these a little bit before I'm going to evaluate. So same as the last problem, you want to flip that up top, make it positive t to the 1/2, maybe distribute it. That looks pretty nice when you distribute it and simplify, 9t minus 1. And that means when I put my t equals 1 back in there, I get 8. Pretty easy. How about my dy dx? If I do that, put t equals 1 in there, can you see where that's at now? The y dy dx, you can use any version that you've calculated along the way, the original or the simplified, doesn't matter. This one's fine as well. But you get 4, no matter how you shake it. Okay? So there you go. We can actually get the slope. Now what that means, of course, is the slope, the change in y with respect to change in x. You're changing 4, let's say dy dx we're looking at. You're doing 4 units of y per 1 unit of x change. Here you're seeing the rate of change of y going up 8 with respect to the rate of change of x. Because it's like an acceleration thing, second derivative. It's a rate of change of rate of change. Onward, let's keep rolling with this thing. There's equation of a line to a curve at a point. Well, do you remember what you need for the equation of a line? Slope and a point. So let's do that. We got to get a point. The t value is not the point, remember. You got to put it back in to get the point. So you got to put t in there, and you can write it all out, do the calculations. Let's call it x of t and y of t. If we actually sub those in there, you guys know 3 pi over 4. If I do cosine of 3 pi over 4, you're going to get negative radical 2 over 2. If you do sine of 3 pi over 4, that's one of the mid, like 45 degree-ish angles, you're going to get square root of 2 over 2. On the positive, it's on the top side of the unit circle, whereas cosine of 3 pi over 4, you were going left, therefore it was a negative. Okay, so you got those, and don't forget to multiply by that coefficient 3 and 4. There's our points simplified a little bit. There's our point. We're going to use that point along with a slope that we need to now calculate, which means I need a derivative. So you go in and say, all right, got to take the derivative of this thing. dy dx is take the derivative of y with respect to t, then x with respect to t, respectively, as you see here. Simplify if you like. Cosine over sine, you can do cotangent and do something fun with that if you want. You guys know that square root of 2 over 2, those are pretty nice points for tangent and cotangent. You're talking about 1 and negative 1, so if you want to do that, go for it. I'm not going to, but play on if that suits you. So what if I just substitute them in like that? Pull the negative 3/4 out. Cosine of 3 pi over 4, as you know, is going to be square root of 2 over 2, negative, because it's on the left, and then the sine square root of 2 over 2. Do a little division, multiplying by the reciprocal. Those cancel with each other. It makes it negative, 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 makes it a positive 3/4. Cool. We got a slope, we got a point. Now let's put the equation. Now, you may or may not remember, we're going to change the way you look at linear equations because it kind of relates to, remember, series. Do you remember the first two terms in a series is actually the equation of the tangent line for that particular curve that we're representing in a series? Does that sound familiar? Have I ever mentioned that before? The first two terms in a series that match a function are the slope of the tangent line to that series. So here, or to the polynomial we're modeling with a series. So let's do it this way. Let's call the tangent line this L of x term. Well, think of this y minus y1 equals m times x minus x1, point slope form. If I add the y1 to the right, what you get is y equals, that's my tangent line, y1 plus m times x minus x1. Well, that means I'm starting out with y1 would be my first point. So our y1 is 3 radical 2 over 2. So that's what I put there, y1. And then what you want to do is add the slope times x minus x1. And here we are, 3/4 is my slope. X minus a negative 2 radical 2 would be x plus 2 radical 2. And there you are, there's the equation of our tangent line. Have you ever looked at writing a tangent line that way? If you use point slope form and just call it L of x. I don't know, it's kind of slick, and it also relates to that series stuff. The first two terms in a series representing a polynomial is the slope of the tangent, or the equation of a tangent line. So there you are. That's a doozy. Pause, go back, send me some questions, bring them to class, you name it. Let's keep going. Down yonder, number 6, so derivative of the y equation, because find all points of horizontal and vertical tangency. Don't you just go instantly, I got to take the derivative, set it equal to 0 for horizontal tangent? You should. All right, so horizontal tangent, first derivative equal to 0. Vertical tangency, of course, are points of where you're undefined, dividing by 0, vertical asymptote. So what we'll do is take the derivative with that's y prime of t and x prime of t. And what we'll do is when we want it equal to 0 for the horizontal tangent, all you need to do is set the numerator equal to 0. So that's 2t plus 1 equals 0, t equals negative 1/2. There's our horizontal tangent. Vertical tangent is when the denominator is 0, when you're dividing by 0. So there I got that. Well, t is great. I can get t. But I want the points of tangency. So you must plug that back into, that t into our x and y. So our horizontal tangent point, okay, there's my t equals negative 1/2 plugged in. You can simplify when you got some time on your hands. But I want to be legitimate, or kind of intentional about expressing it all written out. We can get a calculator for the rest. Then the vertical tangency is when I put 3 halves in for t in each x and y. And there you are. That's it. Those are points of tangency on the curve vertically and horizontally. That's the story on this. That's a good start. 15 minutes apiece. That's what I'm shooting for, and I hit my mark. See you guys in class.